Bismillahirrahmanirrahim. Today, inshallah, we shall learn some theorems about chords, or chord theorems. I've drawn here before you a circle, we call this circle B, and have drawn out two central angles. Here's angle ABD, which I have drawn like that, and then I have another angle here, CBE, and these two central angles are congruent. So I have a circle and I have two central angles, specifically this one over here and this one over here, which are congruent. The first theorem that we shall learn is about central angle and how they relate to the arcs. Okay, so if two central angles are congruent, like shown over here, if two central angles are congruent, then their corresponding intercepted arcs, then their corresponding interceptor or subtended arcs are going to be congruent. That's the first theorem that we will learn. Again, if two central angles are congruent, then their corresponding arcs will be congruent. The corresponding arcs that are subtended or intercepted will be congruent. This is true if the central angles belong to the same circle or two congruent circles. For example, let's say this is a circle and these two angles happen to be 30 degrees, right, like this. Then these two arcs again will be 30 degrees by definition, because that's how arcs are measured. They're measured by their central angle. So it's very easy to demonstrate that if two central angles are congruent in a circle, then the corresponding arcs will be congruent. So we can write this as, I can say arc AD is going to be congruent here to arc CE because of these central angles being congruent. Now this is true if the central angles are congruent in the same circle, or if they belong to a different circles like this, as long as this and the radii and the circle are congruent. So we can say that if two central angles are congruent, then their corresponding arcs will be congruent like this, as long as they belong to the same circle or the congruent circle. So these two circles should be congruent, because then the radii will be congruent. So here we can say circle A is congruent to circle O, and two circles are congruent if their radius is congruent. So this is the first theorem that we learn. In summary, if two central angles of a circle or of congruent circles are congruent, then the corresponding arcs are congruent. Let me repeat myself. If two central angles of a circle or of congruent circles are congruent, then their corresponding arcs will be congruent. The converse also would be true. That is, if the arcs are congruent, right? If the arcs are congruent, the central angles will be congruent, right? Of the same circle or of congruent circles. So in a summary, you can say that if two central angles are congruent, like this, then the corresponding arcs will be congruent. And if the arcs are congruent, then the central angles are going to be congruent. So it goes both ways. If two central angles are congruent of the same circle or of congruent circle, then the corresponding arcs will be congruent. And if two arcs are congruent of the same circle or of two congruent circles, then the central angles will be congruent. Then the corresponding central angles will be congruent. Now, there's another theorem, the first true chord theorem that we shall learn today, because as you can see, there's no chords in these two particular examples, but the first true chord theorem we learn has to do with this particular scenario. Now here I have a circle, and we can call this, let's say, circle Q for change. We'll call this circle Q. And here I have drawn two chords. Now the theorem here states that if two chords of a circle are congruent, then the corresponding arcs will be congruent. So if this chord is congruent to this chord, then their corresponding arcs will be congruent. All right. Now I'll show you the proof of that in verbally at least. So we can say that if two chords are congruent, then their corresponding arcs will be congruent, and if the arcs are congruent, then the corresponding chords will be congruent, like this. So now we have, this is what we got going for us. If two central angles are congruent, then the corresponding arcs will be congruent. And then if the arcs are congruent, then the corresponding chords will be congruent, and the chords are congruent, then the arcs will be congruent, right? So let's see if we can convince ourselves that this is indeed the case. Now, how do we prove that these two arcs are congruent if we're given that those two chords are congruent? That is, if AB is congruent to CD, how do we prove that the arcs are congruent? Well, this is how we do it. I'm going to draw out here from the center the radii that connect to the endpoints of these two chords like this. Now, these are radii that belong to the same circle, circle Q over here. So therefore, they're all be congruent like this, right? Because all the radius, obviously, of a circle are going to be congruent. So I've drawn the radius here to the endpoints of those arc, or of those endpoints of those chords, or endpoints of the arc. Now, these two triangles, you see, are going to be congruent. The reason they're going to be congruent is by side, 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 because we have these two sides, and the third side is a chord, and it's congruent. So by side, side, side congruency for triangles, these two triangles are congruent. And by CPCTC, corresponding parts of congruent triangles are congruent, we can demonstrate that these two central angles are going to be congruent. Right? So we demonstrated that these two triangles are congruent by side, 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 and by CPCTC, these two angles are going to be congruent. And if the angles are congruent, then the corresponding arcs are going to be congruent, which is what we have demonstrated over here. Correct? So how did we prove that those two arcs are congruent? Well, we demonstrated that these two triangles that we constructed are congruent by side, side, side. And this angle over here, the central angles over here, are congruent by the fact that corresponding parts of congruent triangles are congruent. And because those central angles are congruent, the arcs are going to be congruent like this. So this was the proof of how we demonstrate the arcs to be congruent if the chords are congruent. So now the converse of this, as I said, will be if the arcs are congruent, then the corresponding chords are going to be congruent. So what did we prove so far? We proved that if the chords are congruent, then the arc is going to be congruent. The converse of that, of course, would be if the arc was given to be congruent, then we have to prove that the chord is going to be congruent. And that process, again, is very similar to what we just did. We construct the same triangles, actually, and then we prove that those two triangles are going to be congruent. So how do we do that? You say, well, I'll show you how we do that. So here I'm constructing the two triangles again. In this case, we're not given that these two chords are congruent, but instead we are given that these arcs are congruent. Well, if the arcs are congruent, then the central angles are congruent from what we just learned over here. So because those arcs are congruent, we can say that these two central angles are going to be congruent. And then we just said that this is a radii that belongs to the same circle. So all of those radii will be congruent like this. Correct? Let's put it like 3. I'm running out of stickies here. So now we have side, angle, side, and these two triangles are again proven to be congruent by side, angle, side. Right? So now we prove that these two Now they've proven that these two triangles are congruent by side, angle, side congruency for triangles. So these two triangles are congruent. Now by CPCTC, then these two, the red side, so to speak, the chords are going to be congruent. So here we used side, angle, side to prove the triangles to be congruent, and by then by CPCTC, corresponding parts of congruent triangles are congruent. We have proved that those chords, the bases over here, this one, are going to be congruent. So here we demonstrated the theorem. The theorem is as follows. Again, in a circle, if the two chords are congruent, then their corresponding arcs are going to be congruent. And the converse of that, if two arcs are given to be congruent, then the corresponding chords are going to be congruent. And then now we can summarize that over here. See, in a circle, if we are given that if two chords are congruent, then their corresponding arcs are going to be congruent. And if the arcs are congruent, then the corresponding chords are going to be congruent. Correct? And then from here, of course, if we can also demonstrate the following, right? Because if you demonstrate the chords to be congruent, we can, same way, the arcs are congruent. If the arcs are congruent, we can demonstrate the central angles to be congruent. So we can make this nice little diagram here, the relationship between congruent central angles and congruent arcs and congruent chords. And we can, this is like a big, huge congruent, proving congruency circle, so to speak. Right? So in summary, if two central angles of a circle are congruent, then their corresponding arcs will be congruent. And if two arcs are congruent, then the corresponding central angles are congruent of the same circle or of congruent circles. And then if two arcs are congruent, then the corresponding chords will be congruent. And the converse of that, if two chords are congruent, then the corresponding arcs will be congruent. And as you can extrapolate from that, if two chords are congruent in the same circle or of congruent circles, then their central angles will be congruent, the corresponding central angles. So this is like a very, very important concept here to remember. This is like 6 theorems in one. The next thing that we should learn is as follows. The next concept that we should learn is about how a diameter or how a radius interacts with a chord. So you can talk about chord theorems, right? And then you can talk about how chords relate to central angles and arcs. So these are chord theorems as they relate to arcs and central angles. And the next set of theorems are going to be chord theorems as they relate to diameters and radii. You can think of it that way. You can organize the knowledge in that fashion. Chord theorems that relate to arcs and central angles, and chord theorems that relate to diameter over here, which you see, and radii, which you see over here. So now what's the relationship between chords and the diameter? Well, nothing exceptional except for exceptional scenarios. So here's a diameter. The brown segment here is a diameter. It goes to the center of the circle. If you recall, a diameter is a chord of a circle that goes to the center of a circle. The relationship between the diameter and a chord is very, very special if the diameter is perpendicular to the chord. So let's label some of these points. Let's label this point A and this point B. Let's call this circle Q. And let's call this point over here C. And let's call this point over here D. And this point is very special right there. I'm going to label that point M. So now this relationship is particularly important, you'll see, because if the diameter is perpendicular to a chord, then it will divide the chord into two nice, happy, congruent pieces. Again, if the diameter is perpendicular to the chord, it will bisect the chord or divide the chord into two like this. See, another similar theorem here that you see is very similar. In this case, we have a radius instead of a chord, which is not that different because radius is basically half of a diameter. If a radius is perpendicular to a chord, then it bisects the chord. Now, this is not true of any other ordinary chord. For example, here's a chord, right? This diameter does not seem to be dividing this chord into any particular, two halves. No, this will only occur if the diameter and the chord are perpendicular. If a diameter is perpendicular to a chord, then the diameter bisects the chord and also the corresponding arc. Because that's intuitive, we should not prove this, but if the diameter is perpendicular, it does two things. It bisects the chord, but it doesn't stop there. It also bisects the arc that the chord makes, and that's easy enough to demonstrate, and it's kind of intuitive. Perhaps you can prove that. But the theorem is easy enough to understand. How is a diameter related to a chord? Well, the diameter is very specially related to a chord if the diameter is perpendicular to the chord, or you can say if the chord is perpendicular to the diameter. If a chord is perpendicular to diameter, then the diameter bisects the chord or divides it into two happy congruent parts. And the diameter not only bisects the chord, but it also bisects the corresponding arc that goes along with the chord. And this is also reasonably easy to prove. Okay, how do we prove this? So the point is, how do we prove that this diameter is going to divide the chord into two equal parts? Well, let's see. Well, as I said, if you want to prove things to be congruent, you might as well draw out some triangles, because if you can prove triangles to be congruent, then you can prove a lot of other things to be congruent by CP/CTC. So let's let's draw out some triangles. So I've created this triangle, and this is a radius, so this is going to be congruent. So let me draw out the radius in red. For some reason, I like to draw the radius in red over here. Let's draw this radius in red. So now we know the radii are going to be congruent like this. And we're given that this is angle is 90 degrees, correct? And so we have an angle here, and this side over here, of these two triangles right here, there's one triangle and there's two triangles, correct? So we have constructed two triangles by drawing these radii. Here's one triangle, and here's the other triangle, correct? Triangle AQM and triangle BQM over here. And these two triangles are going to be congruent because they share a common side like this. Okay, by reflexive property, QM over here is going to be congruent to itself. So this is congruent to itself, and by hypotenuse leg, okay, that's the hypotenuse of these right triangle. By hypotenuse leg, okay, these two triangles are going to be congruent. And if those two triangles are congruent, then by CP/CTC, these two segments are going to be congruent, correct? So the triangle AQM is going to be congruent to, let me just write down, triangle AQM is going to be congruent to triangle BQM by hypotenuse leg. And then by CP/CTC, I like saying that, CP/CTC, the corresponding parts of congruent triangles are congruent. We get AM, that's this segment here, is going to be congruent to BM. And if a line divides a segment into two parts, then it bisects that segment. So as you can see, this diameter divides the chord into two congruent segments. So that's how we prove that the diameter bisects a chord if it's perpendicular to the chord. Now, as I've suggested over here, the same is true with the radii, because we really don't need the whole diameter to make the proof, right? Because in this case, I could just draw out the triangle here again, like this, and then I can prove these right here to be congruent, and then I could prove that the chord is bisected by the radii. So if the radius is perpendicular to a chord, or if the diameter is perpendicular to a chord, then the radius and the diameter will bisect the chord, correct? All right, so these are two very important theorems. So we can summarize it as follows. If a radius or diameter is perpendicular to a chord, then the radius/diameter bisects the chord. Now, there's a slight nuance to this, and if you appreciate this, you'll understand something quite remarkable. The corollary is, if you have two chords in a circle, such that one of the chord is a perpendicular bisector of another chord. Look at this. If you have two chords in a circle, if one of the chord is a perpendicular bisector of the other chord, what does it say about this first chord? Yep, I believe you got it. So if you said the first chord is a diameter, you would be correct. So in a circle, if one chord is a perpendicular bisector of another chord, then this first chord is a diameter, is one of the diameters of the circle. Of course, a circle will have infinite number of diameters, right? Because there are infinite number of points. But if in a circle, if one chord, because the diameter is just one of the chords of a circle, is a perpendicular bisector of another chord, then the first chord would be the diameter of the circle. So these are two theorems that relate to chords and diameter and radius. And finally, I want to finish with this one last theorem. I have a circle over here, and as popularly, let's call this circle Q. So we have circle Q over here, and I've drawn two chords over here, chord AB and chord CD. And these two chords are congruent. So given here that chord AB, the segment AB, is congruent to segment CD. So these two are congruent segments, so therefore they are congruent chords. Okay, then what can we say about the distance from the center of the circle to these chords? Well, if you remember, the distance from the center of a circle to a chord is measured by the perpendicular distance. That is, you draw out this distance at a perpendicularly here. That's how you always measure distance, the perpendicular from a point to a line, like this. So what can we say about this particular distance right here, or the length of this particular small segment, right? Well, if two chords are congruent, then intuitively, then this distance here, right, should be congruent, and that is indeed the case. If two chords are congruent, then they're equidistant from the center of the circle. So let me write that first, and we shall try to demonstrate that. And it's always nice to think about theorems as conditional if-then statements. If two chords are congruent, then they are equidistant. Now, that's the same way of saying that they're same distance from the center. Then they are equidistant. That's E-Q-U-I. Equidistant from the center of the circle, right? Equidistant from the center. So if two chords are congruent, then they are equidistant from the center. And that's very intuitive, and let's see if you can try to prove that. Okay, so so this is going to be a question mark over here. We won't know quite sure if that's the case, right? So let's see, let's put a question mark. Are these two congruent? Well, we know that the chords are congruent. Now, how would we demonstrate this? Well, over here we just learned that if the radius is perpendicular to a chord, then it bisects the chord. If that's the case, then this is a radii over here, because you can just extrapolate this because it's coming from the center. Then it's going to divide these two chords into congruent segments like this. Correct? So because if the chords are congruent, then the bisected segments are congruent. Then you can construct these right triangles over here like this. Right? And these right triangles will have the same radius over here, correct? Because it's the same circle, the same radii. And then you have made these two right triangles right there. There's one right triangle and there's another right triangle like these. And those two right triangles are going to be congruent by, again, a hypotenuse leg. Hypotenuse leg. There's the hypotenuse, which is the radius, and the leg, which are the bisected segments of the chord. By demonstrating that the two chords, the two triangles are congruent, we can say that this segment over here, the distance from the center to the chord, are going to be congruent by CPC/TC. And since those are congruent, we have demonstrated that the chords are equidistant from the center. Let me review that proof again just to make sure that I've made myself clear. The way we demonstrate that these two chords are equidistant, or that this distance is the same, is by suggesting first that we measure distance by measuring perpendicular distance. So we draw those two distances out. And then we learn here that the radius divides a perpendicular radius or perpendicular diameter divides the chord into two equal parts. So it's going to divide this part over here, and these are all going to be the same length. And if that's the case, then if we draw out this particular radii and complete these two right triangles, these two right triangles are going to be congruent, because that's the hypotenuse, which happens to be the radius, and this leg here, which are the two segments, the congruent segments of the chords, will be congruent. And then by CPC/TC, these two yellow segments are going to be congruent. And we have demonstrated that if two chords are congruent, then they are equidistant from the center of the circle. first we learned that if two central angles of a circle or of congruent circles are congruent, then their corresponding arcs are congruent. That we learned over here. If two central angles are congruent, then the corresponding arcs are congruent. And the converse of that is also true. If the arcs are congruent, then the central angles are congruent. And then we suggested that if two chords are congruent, then the corresponding arcs will be congruent. That we demonstrated over here. Here the two chords are congruent, then the corresponding arcs are congruent, and the converse of that, if two arcs are congruent, the corresponding chords are congruent. So we established this relationship between chords and arcs and central angles. It's very easier to remember that, I think, if you think of this like a circular type of relationship. And then we talked about special relationship between diameters over here and chords, and special relationship between radius and chords. In one particular circumstance, that is when the diameter or the radius is perpendicular to the chord. In that case, the diameter or the radius will divide the chord into two congruent segments. That is, it will bisect the chord. Finally, I suggested to you that if two chords are congruent, then they are equidistant from the center. That is, if these two are congruent, AB is congruent to CD, then they will be equidistant from the center of the centers. If you call this like M over here and N, then QM here will be congruent to QN, right? Like that. So if two chords are congruent, then they will be equidistant from the center of the circle. So these are some very important theorem, and I believe they're all reasonably intuitive, and I hope you mastered this. Until next time, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.